Hi everybody, it's time for the last of the content-rich videos on nomenclature. We are working on step 4, which is stereochemistry. You've run into this before. You recall that E and Z is how we indicate the arrangement of stuff around carbon-carbon double bonds. And R and S is how we talk about the arrangement of stuff around chiral center. Now, this video is going to be a pretty long one because going through E and Z and R and S takes a little while. So if you haven't already, make yourself some popcorn, grab a piece of paper, and we will work our way through it. Now, to start off with, we're not going to actually directly talk about stereochemistry. We're going to talk purely about the ranking system that we use, which is called the Coningle-Prelog rules. It's a very simple way to rank groups around a stereochemical region and give them priority so that we can see who wins, who loses, and what the consequences of that are. Now, if you go Wikipedia and you read Coningle-Prelog rules, which actually I recommend you do, it's not a bad article, it's fairly complicated looking, but it's actually not. It's quite simple. You just have to be super brutal methodical about it. You will end up with priorities that are not instinctively right. So you can't just run with your instincts, at least not until your instincts are well trained in Coningle-Prelog rules. For example, how big a substituent is has virtually nothing to do with who gets the priority. So Coningle-Prelog rules boil down to purely what has the highest atomic number. If we're looking at single atoms as our groups around a stereocenter, for example, or on either side of a pi bond, that's quite straightforward. If you compare hydrogen versus carbon, hydrogen's atomic number is, of course, 1, carbon's is 6, carbon wins. Straightforward. Highest atomic number. If you were to take carbon versus oxygen, carbon is 6, oxygen is 8. Note those are atomic numbers, not atomic masses. Oxygen is going to win. Sweet, that's easy. Chlorine versus fluorine. Chlorine is 17, fluorine is 9, chlorine wins. So if we were to rank these in a 1, 2, and the first one, carbon would get 1, hydrogen would get 2. The second one, oxygen would get 1, carbon would get 2, and chlorine would get 1, and fluorine would get 2. So straightforward, right? The problem is that we often have to break ties. The ties are almost always carbon against carbon. When that happens, we have to walk methodically one atom at a time away from the center. That is a process that is simple, but it is not intuitively satisfying. The good news is it works quite well. So if you are comparing, for example, remember that squiggly line means attached to something, and in this case, the stereocenter, either the sp2 carbon or the sp3 chiral carbon. Let's take this guy, has a hydrogen, let's put another hydrogen, and then a carbon with a hydrogen and 2 methyl groups. So that's a isobutyl group. And we're going to compare it with a carbon with a hydrogen and another hydrogen and a hydroxyl group. We go out, we'll go to the first atom. This is carbon. That is carbon. That makes for a tie. That's okay. That happens all the time. Now we want to move out one more atom, and we choose that atom based by what will win. What is going to be the next possible thing to look at. The quickest way to do that for each of these, well, for generally all these situations, is to say, okay, I've got this carbon right here. It is attached to an oxygen, a hydrogen, and a hydrogen, and that is in order of atomic number. Oxygen, hydrogen, hydrogen. We do the same thing for the other one at step number 1. Here we have carbon, hydrogen, hydrogen, C, H, H. Now we look at just the first of these to start with. In this case, that is carbon versus oxygen. So the oxygen is clearly going to win. That would be priority 1, our methoxy group, our methylene oxy group. And the other one would be ranked number 2. And if we end up with a tie at that point, we move out one more atom and do the same thing. If we're still tied at that point, we move out one more atom and do the same thing. It is not a hard process, but it is a brutally methodical one. You cannot jump a couple carbons ahead and hope that you're going to make it win, because you'll be right about half the time, which is about as good as just taking a coin out of your pocket and flipping it. Now, I jumped a lot of pages. Here's a fun one. Let's take a carbon, which is attached to our stereocenter, whatever it is, CH3, H, CH. We'll put an ethyl group here. CH, alcohol here, H. And we will compare it with, that's meant to be a little squiggle, there we go. This guy, we'll put an ethyl group here this time, oops. And a C with a hydrogen, and CH3, and a T-butyl group, which is a carbon with 3 methyls on it. Now, we start out again. Point of attachment, this carbon versus that carbon, we are at a tie. Going forwards, away from the stereocenter, we say that this carbon here has carbon, it has another carbon, it has a hydrogen, so that's a CCH. This one here, carbon, carbon, hydrogen, also CCH. I did that on purpose. So rats, we've got a tie. In both of these cases, we have multiple directions that we could go in. The idea is to go the direction that makes that team win, or at least gives it the highest chance of winning. So in all of those cases, that's going to be proceeding horizontally, but that isn't actually always true. We move out to this carbon versus this carbon. We don't count backwards to the other C. There is one exception to that, which is multiple bonds, but we'll get to that later. This one is attached to a carbon. It's attached to a carbon. It's attached to a hydrogen. It's another CCH. Oh, there we go. This one, carbon, carbon, hydrogen. What a coincidence. We had another tie. So let's go out a third carbon. Now we have an oxygen, a hydrogen, a hydrogen. We go out a third carbon. We have a carbon, a carbon, a carbon. Now, again, this is brutally methodical. We do not look at the body of evidence. We don't say OHH versus CCC and start thinking maybe CCC is going to win. We start with the very first one, the oxygen versus the carbon. Oxygen wins. We don't look beyond that point. It doesn't matter what else is attached. We've reached the point where it's a winner. It is not a body of evidence. It's one evidence point that makes it win. So in this case, this guy would get priority 1 relative to the other one. Now, what to do when you have multiple bonds? That's a very good question. I'm glad you asked. So if I have let's scroll that guy up there. If I have a carbon that's attached to something and it has a double bond, now what else did I put there? Oh, just more hydrogens for fun. Pi bonds get treated as another bond to the same element. So if I have a carbon-carbon pi bond, I count the sigma bond as an attachment to carbon. I count the pi bond as a second attachment to carbon. So you will always have 4 substituents, even though it is both carbon, even though it's a pi bond with only 3 substituents. Now, to put that into practice, if I was to do the little game that I've been doing here of the little letters for each possible atom, this carbon has the bond to carbon, the other bond to carbon, then the hydrogens. That makes C for the sigma bond, C for the pi bond, H. That I think is fairly logical. It gets a little bit less logical when you move to the next one because you actually go backwards once along the chain, which we don't normally do. We're normally looking forward at all times. But if I take this one, I count not the sigma, because that would be technically going backwards, but the pi would be my first carbon, and then there's 2 hydrogens, that one and that one. You can think of that as being equivalent to a ghost C, another ghost C, where these 2 ghost C's are due to the pi bond. Of course, it's not always a carbon, because I could have had a carbon-oxygen pi bond there, in which case it would be an oxygen we were adding as the ghost, not the carbon that we'd be adding as the ghost. So pay attention to the atoms on each side of the pi bond. Now, let's do a quick comparison and actually rank something. We'll take this guy versus something more similar to what we did earlier. Now, here we have carbon versus carbon, our first tie. This carbon has a carbon, the ghost carbon from the pi bond, and a hydrogen, so that'd be CCH. This carbon here has a carbon, a hydrogen, also CCH. When I go to the next one, it has a carbon, it has the ghost carbon going backwards, and the hydrogen. CCH. I move out to this one, it has a carbon, a hydrogen, and a hydrogen. So this side gets the priority win. Not too hard, I think. Takes a little practice, like virtually everything interesting does. Now, that is in a nutshell the Cahn-Ingold-Kralog rules and how we apply them. It's a system that always works. It is a system that gets challenging in some cases, but not cases we really care about in this class. So let's move to applying this into E and Z. E and Z is how we describe stereochemistry around a pi bond. Let me take a flavor molecule that you're all familiar with. This is cinnamaldehyde. How we would generally draw it. It has a pi bond in it. This pi bond has a specific configuration, and it would be different if the configuration around it was different. That's actually true. When we do E and Z, the steps are divide your double bond perpendicular to its axis. So we do not compare the way I have this drawn, the left to the right. We compare the right to itself. We compare the left to itself. Then we come up with a system of priorities. So here we are going to do two comparisons. All right, step one, divide the bond. So compare two subs on the left to each other and pick a winner. Step three, exactly the same as step two, but the two on the right. As I'm sure is clear, it doesn't actually matter that you start with the left and finish with the right. You could do it either way. Step four is look at the relationship between the winners. If they are cis, it is Z. If they are trans, it is E. E and Z are the first letter of two German words for on the same side or on opposite sides. It is a little inconvenient that those don't translate easily into English and keep the same two letters. You can think of it as Z could be Ze are on the same side. Je suis en France maintenant, donc on pourra faire l'accent. Or you could also say that the one that is shaped like a Z when they're trans is E, and the one that's shaped like an E where they're all on the same side is actually Z. And then remember that everything German is a little backwards of what you're familiar with. That works too. Or you just brutally memorize it. Whatever makes you roll. So if we look at this molecule, it's going to be a fairly straightforward set of comparisons. When I compare the two on I said I'd start on the left. You were comparing a hydrogen to a carbon. That is an easy comparison. In this case, the carbon wins. So we'll put a little asterisk there. If I win, I get a star. Same thing on the other side. I compare a carbon to a hydrogen. The carbon is clearly going to win. It doesn't matter that it has a carbonyl. It's already won. So we get the asterisks on the carbon. Those two carbons, are trans to each other, opposite sides of the double bond. Now, that means if they're on opposite sides, that it is E. And it brings together a really interesting question. Why do we have E and Z when I could have just said trans? And way back in the day, they did often just say trans. It's a fair question, except that they describe different things, and it doesn't always work to switch one with the other. We have E and Z, which is a property of a bond, and we have cis and trans, which describes a relationship of two groups around that bond. When you get to more complicated molecules, you will see that it's not as obvious as this one if it is a cis or a trans, because you'll have two important looking things on the same side of the bond. It's easy to ignore hydrogens. It's hard to ignore, for example, a ring. So even if it wins, you wouldn't end up with a logical nomenclature there. So when we talk about this hydrogen here and its relationship to this other group over here, we would talk about them being either trans or cis to each other. But that's not a property of the pi system. It is a relationship between two things that are engaged in the pi system. So if it's a relationship, we use cis and trans. If it is describing a pi system, we use E and Z. Organic chemists do sometimes break that rule, but we know we're breaking the rule and we're just saving ourselves a little bit of pain. Also, cis and trans doesn't uniquely get used for pi systems. With ring systems, for example, we talk about two hydrogens being trans-diaxial if they are 1,2 trans. So you've run across that before. But when we talk about the name of a molecule, we will use E and Z if the pi bond is asymmetric. So if we were to give a name to this thing, our step 1, very straightforward, it's an aldehyde. Our step 2, also pretty straightforward, it is a prop 2-ene, which you can actually just do as 2-ene. We have 1 substituent, 3-phenyl, and our stereochemistry, which I skipped to the head, sorry, is E. That E is at the 2 position, which is the only position. So this would be either E, 3-phenyl propanol. You might ask why I didn't put the 2 in there. You can't actually put that pi bond anywhere else. So it is redundant to write the 2. It is not wrong, in my opinion, to write the 2. But it is redundant and you don't need it. If you had written, for example, 3-phenyl prop, we're good. That's nice nomenclature, and actually probably how I would have written it. So that's how you do E and Z on a very simple example. Why don't we try a harder one? I'm sure all of you today have had your carrots or potentially your liver, both of which are rich sources of vitamin A, which is retinol. Retin for retina, because it's used as the precursor for the photoswitches in your eye. It's a lovely terpenoid structure with a lot of pi bonds. We will focus on 2 of them, but we actually have the tools to just flat out name this thing. Sorry, pi bond there, alcohol there. This is retinol, or vitamin A. The 2 pi bonds that I want to focus on is we'll start with a straightforward one. That guy there has 3 substituents on it that aren't hydrogen. So I think at a glance you can see how it's going to end, but it's good to go through the process. Here we have a more complicated one where there are no hydrogens directly off the carbons forming the pi system. And we'll have to bust out our mad ranking skills to take a better look at it. So let's start first with the one on the right that's fairly easy. Draw in the hydrogen. It's always a good plan so that you don't make a silly mistake. We are going to compare first the things on the left, then the things on the right, then the relationship of the winners to each other. So on the left, we have carbon versus carbon. That is a tie. This carbon is a methyl group. It is attached to H, H, H. This carbon is attached to carbon, the ghost carbon because of the pi bond, and hydrogen. Now we're going to end up with a fairly straightforward winner because we start out with H versus C. Mission accomplished. Let's put our asterisks down. Other side, much more straightforward. We are purely comparing a hydrogen with a carbon. H versus C. C wins. Those 2 things, their relationship is that they are trans. So the stereochemistry is E. Play around as an exercise for yourself. The other 3 that are in that chain are all E. Next one, it's more fun. I'm going to draw it a little bit bigger here so we have room to play. I'll put that squiggly line to show that the molecule continues on further, but we're not going to bother drawing it because I know the tie will be broken by then. We split this up. We'll look first at the bottom, then the top. Why not? We start with a tie, carbon versus carbon. This carbon is a methyl group. It has 3 hydrogens on it. Moving forward. This carbon has a carbon and then 2 hydrogens. We have a winner, so let's put our asterisks down. completely independently. Let's look at the other side of the pi bond, which in this case is the top. We have a carbon versus a carbon. That is a tie. This carbon is attached to a carbon, another carbon, and a third carbon. This carbon here is attached to a carbon, a ghost carbon because of the pi bond, and a hydrogen. Sorry, that's supposed to be C. That is an interesting finding. We start out this versus that, still a tie. This versus that, still a tie. Carbon versus hydrogen, this side is the winner. Even though the other side is ginormous. It's got 5, 10, lots of carbons in it. And an oxygen. And lots of pi bonds and stuff. But remember, we don't look at the body of evidence. We methodically go one atom at a time. So we have this guy and this guy as our two winners. That makes this one cis. The two high priority groups are cis to each other. And that makes the actual pi system Z. Cool, hey? We could at this point very easily name it. We have the functional group as an alcohol. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a nonanol, non-tetraenol as our parent hydrocarbon. You know, let's just do it. 1, alcohol. 2, non-tetraene, where the alkenes are on bonds 1, 2, 4, 6, and 8. If that was unclear, flip back to an earlier video on parent hydrocarbons, 2 videos ago. Take another peek at it. My substituents, oh, look at this salad of substituents. I have 1, 2, I have dimethyl at carbons 3, 1, 2, 3, 4, 5, 6, 7, 3, 7 dimethyl. And I've got this thing. This thing is a cyclohexene eel. It has methyl groups at positions 1, 5, and 5. Sorry, 2, 6, and 6. Okay, and 4. We have 4 of those suckers are E and 1 Z. And the 1 Z is on the substituent. All right, that's going to take us a while. I'm joking. It's not going to take us any time at all because we've broken it down into the 4 steps and come up with all the information that we need for our molecule here. The cyclohexyl group is going to come before the dimethyl in the name. We have a non-tetraenol. So let's start with that over this side. That's our 4 pi bonds that are in the linear system. It's a 1-ol. The carbon number 1 is our alcohol. Our substituents, this is not going to fit in my little piece here, but we'll give it a good go. We have, that is going to be, one of my substituents is 2, 6, 6, trimethyl, cyclo, hex, 1E, ene, eel. So the 1E ene is where the pi bond is. Sorry, 1Z. The eel indicates that it is a substituent on the non-tetra enol, big old parent hydrocarbon there. And then we have our 3,7 dimethyl. Now this doesn't all fit on one line. these would be attached to each other as one thing that I do not have the handwriting to fit into one line. But if I was to read it aloud to you, it's a little story, bedtime story, it would be 2,6,6-trimethyl-cyclohex-1-Z-enil-3,7-dimethyl non-tetric 2E4E6E80-ene-1-all. Done. That's vitamin A. Now, we're like a half hour into this, and we're just getting into the RNS section. And you're thinking, oh my goodness gracious me, how long can this go? I'm wondering the same thing, to be honest. However, we've done many of the hard steps already. We are good at prioritizing. We are now good at using those priorities to compare groups to each other to come up with some stereochemistry. What we have left to do is to extend this from ranking between 1 and 2, which is what we do with pi bonds. And now we have to rank the 4 things around a chiral center that is a carbon. We are going to start very abstract. We are going to say that we are going to have a theoretical molecule. Our molecule is going to be made out of candy because I'm in France and I don't have my molecular model kit. And we are going to work on RNS, starting out with just, let's see if I can put that somewhere where it's easier to see, with just one tetrahedral carbon with 4 different things that we are going to prioritize based on my perception of how good they taste. And carbon has to be black. We all know that, right? Everybody agrees? Carbon is black. So let's make our priority list. We don't count the carbon, so that won't be in the list. But my 3 colors will be 1, pink, 2, green, 3, yellow, 4, blue. That is actually the first step of assigning RNS. Step number 1 is assign priorities. We've done that. Here's my winner, pink. Here's my second place, green. Third place, yellow. Fourth place, blue. Step 2, arrange the molecules so that priority number 4, the lowest priority, is to the back or away from you. So here, looking at the camera, that would be like this, where I have the blue, which is my lowest priority, to the back. I have my 1, which is pink here, my 2, which is green there, and my 3, which is yellow here. Once you have the lowest priority to the back, you count 1, 2, 3 around the circle that you can see here. 1, 2, 3, pink, green, yellow. That is a clockwise turn. That's the critical step. So count from 1 to 3. See if it is clockwise, which is R, or counterclockwise, which is S. There. Uh-oh, molecule's falling apart. Might have to eat this one and start from scratch. So here, 1, 2, 3, pink, green, yellow. You obviously don't count the blue because you did its job by sticking it away from you. I know it's towards me, it's away from you. That is 1, 2, 3, or clockwise. This should work always because I always have to take this thing and rotate it so that the lowest priority group is away from you. If the lowest priority group is towards you and you do the same count, 1, 2, 3, you get counterclockwise. That would be wrong, is the word that you're looking for. The group has to be away from your point of view. Yes, you can mentally change your point of view anytime you want. That is a possible way to do all of these. I get asked that all the time. So to the back, 1, 2, 3, clockwise. If I was to hold it slightly differently, to the back, 1, 2, 3. They're in different positions, but it's still going around clockwise. If you take its mirror image, which is of course not superimposable because that is the definition of chirality. Oh, I've lost track who's who. Put it to the back. Count pink, green, yellow. That goes around this way. That is counterclockwise. So it is S. Mirror images are always opposite of each other. So, cool trick. Let's create a molecule. Nice simple one. Let's just take 2-butanol. 2-butanol has 2 enantiomers where the methyl group is up and a hydrogen is down. Now I'm not going to spend any real time on this video talking about the different physics of stereoisomers because we're going to talk about that a heap when we go through chapter 5. That's the bit I want to focus on in chapter 5. Nomenclature is what we're focusing on here. So we're not going to talk about how these two things are different and you might have different sensory perceptions and so forth and so on. We will just accept that they are different things because you've already gone through that sort of stuff in first year and in high school. When presented with 2 things to name, I personally always choose the easiest one to name first because I know that when you invert the stereocenter, you get the other thing. And that is the difference. If you have one stereoisomer, one pair of stereoisomers, one will be R and the other will be S. So we start with our priorities. We have 4 things here: an oxygen, a hydrogen, a carbon, a carbon. We have 2 clear rankings and 1 tie. Oxygen is 1. Hydrogen is going to be 4. That is often, though not always, true. Now we have carbon versus carbon. This carbon is HHH. This carbon is CHH. This one becomes our 2. This becomes our 3. I chose this one for a reason. The reason I already told you. It's the easy one because the hydrogen is already to the back. That is what's meant by those dashes, is that the hydrogen is away from your nose. And in this case, that methyl group is towards your nose, and the other 2 groups are in the plane of the paper. So here, hydrogen's already in the back. I can directly count around this circle. 1, 2, 3. That loop is counterclockwise. This is S. If I were to do the same rankings with this one, 1, 4, 3, 2, I have a trickier problem. I could take the correct jujube, so that is my 1 and my 4. I could take my jujube that is set up as this is, where I have my 1. It's a little hard to see, but there you go. I have my 4 at the top. I have my 1 where the OH is. I have the 2 where that ethyl group is. I have the 3 down where that methyl group is. I can take that and arrange it so that the hydrogen is to the back. Then count around 1, 2, 3. That is R. Perfectly valid approach and a good approach. You can also, if you are good at 3-dimensional things, mentally put your eye on the other side of the computer screen or piece of paper. That is a trick that is learned. It's not inherent. If you can't do it now, you can learn to do it. That was true of me. I remember the process clearly, actually. And that will work too if you have a good 3-dimensional sense or develop a good 3-dimensional sense. you'll find that that is something that can be used no matter what the situation is, and it's fantastic. That being said, what I've outlined here also shows you a trick. If you take any two groups, so here's my two things, they are chiral and they are enantiomers. If I take any two of those groups and I switch them, you will get the enantiomer. So theoretically, if I switch these two, it is superimposable upon this, which it actually is superimposable on that. So that means if I switch any two groups, I have changed it from R to S or S to R, but to the other. I can determine its stereochemistry and then know that I'm exactly wrong. That sounds confusing, but it's actually a really easy way to do this. So if I just take this, switch two groups, and for the record, we always take the number 4 and switch it with whatever is in the back. So here, I would take the number 4 and I would switch it with that methyl group. We now know that this is not the molecule I started with. It is the opposite stereochemistry at that center. We've made this guy. We count around it. 1, 2, 3, 4. That is S. We knew that because we did it with the first molecule, but go through the process anyways. It's good for you. If it comes out S, the answer is the opposite. Because you know you switch those two, which produces the opposite. So you can think of it as a double reverse strategy. Switch and bait is another way to look at it. You know that the thing that you drew is not your thing, but you can figure out what your thing was from it, and it's much easier. This trick is particularly useful for large cyclic molecules, and we'll do an example of that. Let's take two examples. One of them is we're going to do a little talk about meth's good side. I thought the title was particularly clever. It turns out that meth, which one obtains as a racemic mixture, so half of one enantiomer, half of the other, one of them is the bad meth, and the other one is a good meth. Let's look at them both. This guy is good meth. This guy is bad meth. This is the one that is addictive, produces sensations of euphoria. Generally bad news. This one, on the other hand, is an over-the-counter nasal decongestant in a spray, sprayed up your nose. Over-the-counter, you can just buy it. Don't get too excited. It's tough to interconvert the two. You're not going to get rich by buying nasal decongestant and converting it. It is also the active metabolite of the Parkinson's drug, selegiline. It's not addictive. It produces no euphoric effects. Their effects are completely and totally different. So if you were looking for one of these, you would definitely want to know what stereochemistry you're buying. So let's do a little bit of nomenclature. I like to start with meth because the hydrogen is already to the back, though it's certainly not necessary to do so. So we have nitrogen, hydrogen, carbon, carbon. So we have a very clear 1. We have a very clear 4. This is HHH. This is CHH. This one becomes R2. This one becomes R3. This one is then going around the circle counterclockwise. So it is S. And if we were to combine that with the name that we have already done, that is S, N-methyl, 1-phenylpropylenanamine. That's the full name of that molecule. And the other one, similarly, would be R, N-methyl, 1-phenyl, propan 2-amine. I did that directly on the page because it's easy. You can use bait and switch. You can use your molecular model kits, which, quite frankly, you can use in your exams because I want you to understand the concept far more than I want you to waste a lot of time trying to do stuff. You can use jujubes and toothpicks, though I find that they're a little folly-aparty and they tend to correct and then you get stuck eating them.